Okay, thank you. All right, thank you, everyone. Let's get started. We're very happy to have Dr. Alankrita Bhatt with us from Granica AI. She received her BTech degree from IIT Kanpur in electrical engineering, PhD from UC San Diego, postdoc at Caltech and science, and recently she joined the AI startup. So her interests are in information theory, statistics, data science.
All right. Thank you so much for the invitation and thank you all for being here. I'm Alankrita, and in today's talk, I'll start off by giving you an overview of my broader research program and then kind of go into one of my recent works to illustrate the kind of problems I work on. Okay, so clicker is not working. Okay, now it was. Yeah, so let's start off on an inspirational note with the following quote by Laplace, who also told us that the probability that the sun will rise tomorrow, if it has risen continuously for n days, is equal to n plus 1 over n plus 2. And I will later tell you that there is a principled reason why it must be this. And this is perhaps one of the first examples of sequential decision making, where you're trying to make some kind of forecasts about an uncertain future based on information you observe about the world one day at a time. So like Laplace, we deal with a lot of sequential decision-making problems across science and engineering in domains like robotics, where you're trying to step-by-step navigate a robot to reach a certain location, predicting whether it will be sunny or rainy each day, and in finance, where each day you're trying to allocate your resources to maximize the amount of wealth you make over some time. And kind of the bare bones essence of each of these problems can be distilled down into this schematic below, where there is a decision maker, that's going to be us in this talk, who at each time takes an action, such as predicting whether the weather will be sunny or rainy, and then receives some feedback about the quality of their action from the environment, such as noticing the actual weather and seeing whether their forecast was correct or not. And then the next day they take another action and so on. This continues for some long time horizon. And the objective of the decision maker is to design a policy that tells how to take an action at each time step in order to optimize some long-term objective. For example, you want to be make as few mistakes with predicting the weather over the course of a year, or make as much wealth as possible in the course of several years, and so on. And what makes this objective challenging is that the environment that you are operating in is often unknown, and sometimes it's actively adversarial towards you in trying to achieve your goal. So we are really dealing with a tremendous amount of uncertainty about the environment. So let's zoom into what this challenge of uncertainty really means. So this is, again, what we are doing in sequential decision making at each step. We have some data that we have observed so far, y1 through t minus 1. Based on this, we are taking some decision at time step t. And when I say uncertainty, what I really mean is that we have no idea about, we have some notion of uncertainty about this source that is generating the data. We don't really know much about what is the source. So just to kind of help orient you a little bit, we might make some assumptions about this source. So for example, we could say, okay, the data is coming from a fixed but unknown probability distribution, and then we could further make some assumptions about the nature of this distribution. We could assume that there is no distribution, but the data is being generated by some entity that wants to make us suffer as much as possible. Or we might kind of make some middle ground assumption. But kind of what each of these are doing is in opposition to a more classical approach, where we assume that we know the exact statistics of this distribution, and then kind of plug in some optimal action for these statistics that we have assumed that the data is coming from. So this will work very well if your assumptions are correct, but it can go very, very catastrophically wrong if your assumptions are really off. So that kind of brings me to the main question that I deal with in my research program, which is how do we make robust and optimal decisions in the presence of uncertainty? And in the sort of path to answering this question, there are a few methodological pillars and themes that turn up a lot, and they're following. So the first one is this idea of universality, where we try to construct probability distribution, which is some kind of universal approximator for the class of, I don't know, source statistics or distributions that we have uncertainty over. And this idea really goes back to Laplace, who taught us how to construct a probability distribution that is universal for the class of all IID Bernoulli processes. And that is where the famous rule of succession that was there in the first slide comes from. And this kind of area connects a lot to applications in data compression, prediction, portfolio selection, and so on. Another question that I've been thinking a lot about is how do we achieve performance guarantees that are a function of some notion of easiness of the data that we have, and we will see this much more today. So we kind of want to detect and utilize any nice structure that might be possibly present in the data and bridge this kind of extreme stochastic or adversarial assumptions. And the third kind of theme that comes up a lot is related to the optimal decisions part of optimal decision making, where we don't just want a good algorithm, we also want fundamental limits of what is and isn't possible in the presence of uncertainty. So we try to establish some fundamental limits and then hopefully develop constructive strategies that will meet these limits. So today I'm going to talk about a recent work that kind of bridges all these, and it's about instance optimality in universal prediction. And this is a joint work with Sid Banerjee and Christina Yu, who are both on the faculty at Cornell OR. Okay, so before I get into the...
One quick question. So should I be thinking of the decisions that are being made as a prediction of the next data point or something? Or
it's some sense. I mean, the example I will give is you are trying to predict what's coming next. Okay. But in general, you could be doing something much more general. You could be forecasting the probability, and then your loss could be something else entirely.
Good question. What is structure? What do you mean by structure?
I'll get more into it. So, for example, you want to kind of understand, is my data possibly coming from a stochastic distribution, and can I adapt to that on the fly? Okay, yeah, so that's a good segue into kind of high level of what I'm going to talk about today. So this is kind of bringing back that taxonomy of uncertainty that I had in an earlier slide. Typically, when we are dealing with a sequential decision-making problem, the first assumption one might make is, depending on the application domain, is to assume that the data will be coming from some fixed unknown distribution or from an actively adversarial entity. Right, so let's say you're trying to design a spam filter and you make the stochastic assumption and say all spam emails follow a similar distribution. That will work mostly well in practice, but if there is somebody who is out there to get you, they can specifically design some new example that can fool you. So this kind of assumption is usually not robust to any strategic actors. On the other hand, you could make a very, very pessimistic assumption and try to design a strategy that is as robust as possible. But usually, like, you sacrifice a few things in the pursuit of this robustness. One is typically like these strategies tend to be much more complex, and also you suffer in terms of performance because you are making a much more pessimistic assumption, right? What we want to do is we want to bypass the need to kind of make this first step assumption about the nature of the environment and to adapt to the nature automatically. And in today's talk, for the most part, I will present a case study in the very, very canonical example of binary prediction. And towards the end, I will talk a bit about how the principles we learned can be developed to more, can be extended to more general sequential settings. Okay, so I'm going to start talking about the model now. So what we will do for the majority of this talk is to predict the next bit that will come in a sequence, right? So you have your data is now the history of the bits you've seen so far. And based on these, you want to predict what bit will come next in the sequence. And we will allow for randomized predictions. So you might output a bit with some Bernoulli P probability, like tomorrow's bit is going to be 1 with 80% probability, or you could always take a deterministic action as well. Okay, so now let's say we have a strategy. How do we think about its performance measure on some data that we have received? So that's going to be given by this quantity called the regret, which is going to be the following. So we are going to look at the expected number of mistakes that our algorithm made. So that is going to be this quantity here, which is just the sum of probability of error at each time step. And we are going to compare our performance to the performance of some adversary who knows the future but is constrained in some way. And the constraint, the very simple constraint that I'm going to consider here for now is there is an adversary that knows the future but is constrained to using the same action each day. So each day you either take the action 0 or the action 1. That is kind of the performance that we want to match, right? And of course, this is something we can't calculate causally at day number t. We don't know what's going to be the best bit at the end of the time horizon. So that's why kind of approaching the performance of this future knowing adversary is non-trivial. And what we want typically is this regret to be sublinear in the size of the horizon, because that means that the average number of mistakes we made is around the same as the average number of mistakes this, fictitious predictor that can look into the future and tailor their decisions would make. So this is going to be kind of the performance measure for our algorithm on a particular sequence. Okay, so this is the model. Any questions about this one so far? Okay, great.
So probability indicated by n or something. So
Sorry?
1 by n indicator you are doing something.
1 by n indicator where?
So the y is hat not equal to y by n.
Yeah, this is like the expected indicator, y hat t not equal to yt.
I think
So
the regret definition is what he's asking about.
Yeah. Is it expected?
Why is y1 in there? Like, I'm assuming that the first outcome is given to you. Based on that, you're looking at the.
so this y hat t can be constructed as a function of y1 through t minus 1.
Oh,
Yeah.
okay.
So each day you can make a prediction based on based in any way on the past. You can't look into the future. So this is the performance measure. Okay, so now we want to be best of both worlds. So let's kind of try to understand more in detail what happens in each world. So first, let's say that the bits are coming from some fixed but unknown probability distribution, Bernoulli P, where P is not half. Okay, so if you knew P, the optimal, let's say P was a quarter, we can take that as our running example. The best thing to do if you know that P is a quarter is to just take the action 0 each day, right? That way you would be wrong a quarter of the times. The benchmark would also be wrong a quarter of the times. So your regret would be basically nothing. So we don't know this. So what we are going to do is a very intuitive idea, which also turns out to be the optimal algorithm, which is called follow the leader, which just looks at what you've seen so far and takes the majority vote. You can break ties arbitrarily, but let's say we break ties uniformly at random. Right, so this is kind of a very intuitive algorithm, turns out to be optimal as well. Now, what is the average case performance? And by average case, I mean expected regret, where the expectation is with respect to randomness in the data sequence. So the expected regret in this case turns out to be constant. And the reason for this is the following. So after a certain amount of burn-in period, if P was, let's say, a quarter, anytime you look back at the past, you're going to see a quarter ones and 3/4 zeros. So after a certain point, you are always going to output 0 if you apply this FTL strategy, right? So after a certain period of time, almost always you are going to follow the same decision that the competitor that can look into the future is taking. Right, so that's why the only time that you will really make a mistake is in the initial part where the statistics have not really stabilized yet. And that has nothing to do with the length of the time horizon. So that's why the expected regret of this algorithm is going to be constant. Right, so that's great because we asked for sublinear regret, but we got constant regret. So, we get something more than what we wanted. So the flip side is if we want to engineer a sequence to break this algorithm, we can. And here is the sequence that you might use. So you can just, if you feed the sequence of alternating zeros and ones into FTL, what's going to happen is that, let's say at the first time step, FTL is going to predict Bernoulli half, right, uniformly at random because there are ties. And so you're going to make half a mistake in expectation. At the next time step, you've seen 1, 0, but no ones. So you are going to predict a 0, but the actual bit that you get is a 1. So you make one mistake, right? So you make half a mistake at every odd time step and one mistake at every even time step, right? So the regret turns out to be linear in the time horizon because the optimal action will make mistakes only half the times, whereas you're making a mistake 3/4 of the times. So in this case, the worst case regret turns out to grow linearly with n, right? So you get very, very good average case performance, but the flip side is you get very poor worst case performance.
But aren't you supposed to compare it with the fixed comparator?
Yeah, so the fixed comparator also will make just half the time mistakes, but you make half plus quarter times the mistake. Yeah. So, okay, so kind of inspired by that, now let's make the other extreme assumption that at each time step, the next bit will be picked completely adversarially. Right, so in this setting, the optimal algorithm was shown by Kober in 1966, and I'm just going to call this algorithm Kober throughout the talk. And this turns out to be also a majority vote, not just of the past, but of the past and a randomly hallucinated future. So you look at the bits you have in the past, and then you fill the future with IID Bernoulli half bits, and then you take the majority of that. So this is going to be a randomized decision for most of the times, right? And how you get this is by looking at the regret minimization as iterated min-max problem, and then do a dynamic programming approach, backward induction to solve this game, right? And then this algorithm will pop out. So how does this do? So the average case performance turns out to scale roughly as square root n over 2 pi, where again, the expectation is with respect to this data sequence, which is good. I mean, it's not constant, but it's not linear. More importantly, the worst case performance, which is really what we designed this algorithm for, is also square root n over 2 pi, which is good because, it means that even if there is an adversary with the worst case sequence, you still, are not going to get into linear regret territory. In fact, with these two, you can see that the regret of this algorithm is going to be exactly the same on every single sequence. So this algorithm has the property of having the same regret on every single sequence. Okay, so let's put these kind of two worlds side by side and see and this can really tell us how the regret profile of these two algorithms kind of is very complementary. So FTL has constant average case regret, but linear worst case regret. And here we can engineer a really, really bad sequence to make FTL incur a lot of loss. On the other hand, Kober has exactly the same regret on every single sequence, regardless of any properties of the sequence. So
sorry, this adversarial thing I don't get. I mean, supposing the adversary just picks yt not equal to y hat t every time. That's possible, right?
Yeah, so for that, the Kober action is going to be randomized at each time step. So it kind of doesn't have access to that randomness. So it has access to the strategy, but not the, yeah. Right, so the FTL strategy has very, very good average case performance, but it's very brittle. And Kober has very non-adaptive performance, but is very, very robust. So it's very, very complementary profile. So there is a very...
Elaborate on what non-adaptive means here?
Non-adaptive means there is no variation with the sequence. So it's not like there is some sequence that's more typical or more easy, so I'm going to have lower regret on that sequence. So it kind of, in some sense, treats every single sequence as equal.
Question here, Rahul.
Yeah.
Does FTRL do any better than FTL?
Yeah, so FTRL usually is too robust, and then you would get again into Kober territory. So you would again get square root n and won't be.
But does it give you average case order 1 and square root n? Is that what you would be anyway?
So FTRL in the average case I don't think so. So later I will have an example where online gradient descent, which is an instantiation of FTRL,
Yes.
gives you bad, is pessimistic.
Okay.
So yeah. So typically, like when you do FTRL or just FTPL, these tend to be kind of much more robust and not very adaptive. Is my sense.
So cohort result is actually more general, right? Because because if you think of the just predicting the sequence, individual sequences, then it shows that there is a function phi, so I can actually put a prior sort of on this. And if I have some idea like where this y is coming from, whether it's coming from some idea or not, then by tuning this function phi, I have a new algorithm that gives you,
Correct. Yes.
Although, I mean, on the average, we have in expectation it is half, but it can be tuned to that particular assumption, not the prior.
Yeah. So I agree with you, and we will kind of get more into that when we try to construct the algorithm. But just because I in this field, so if you kind of try to plug in directly and try to derive an algorithm from cover, it's not very tractable. So we haven't been able to, we tried that route, but didn't really work out. So we try something else. Yeah, but you're right. And you will probably kind of see that result come back when we prove a converse.
Okay.
Yeah.
I don't know, maybe you'll elaborate on this. So is there trying to figure out, is there a reason why this non-adaptive is not a desirable thing to have? I mean,
yes, because if you know that most of the times your data will be very typical, you could have like a constant.
Or you could have hoped for a constant regret.
Yeah, but then again, like if there is some strategic entity, they might mess up very easily. Yeah. Yes.
Maybe a nice question. Is there any reason to hope that? So here, all our notion of how well we are doing is this additive regret, right?
Yes.
Okay, so is multiplicative weight something one should even think of when you're thinking of that's FTR. Oh, that's FTR.
Yeah, so a multiplicative weights algorithm is like you said FTRL, and then you would again get into much more like robust territory. Yeah.
Okay, my nice thing was if you could think of these as two experts.
Oh yeah. So that again, I'm gonna talk about that, but that won't work because if you kind of have these two algorithms as two experts, plug them into multiplicative weight, you also get an extra order square root n regret overhead that already kind of makes the guarantee vacuous. So using exponential weights not a good idea here. Okay, but yeah, I think maybe when I kind of try to formulate what we want, it will be clearer to understand. So what we really want is to have a single algorithm that combines the good properties of both of these. So now I'm going to formally define what we really want. So let's say there was a genie that was able to tell you that for the sequence that you are going to get, whether FTL is the more appropriate algorithm to use or cover is the more appropriate algorithm to use, right? So if you had such a genie, you would be able to get the minimum of the regret of these two algorithms on that particular sequence. But because we don't have a genie, we are going to allow ourselves a little bit of leeway in terms of an extra multiplicative factor in this minimum of these two regrets. And that is what we are going to aim for. We want an algorithm that achieves within some factor of the minimum of these two regrets for every single sequence yn. So in particular, that's, I think, an important part, that we want this guarantee to hold for every single sample path, right? And of course, it's not clear a priori whether this is possible. And of course, we want this competitive ratio factor to be small, because if it's too large, the bound is vacuous and then it's not very useful. So the challenge here really in doing this is that hindsight optimal action cannot be calculated before the end of time. And because that can't be calculated before the end of time, when you are at some middle of the game, you have really no idea how these two algorithms are doing, right? So you can't tell how much partial regret has each algo accumulated so far, because you just can't calculate what is it that you actually have to compare against. And
in most of the cases, these algorithms have adaptive bounds, right?
Yes. So
adaptive bounds mean you can compute the regret, at least an upper bound with the regret in terms of the losses seen so far.
Yes, but you might have sequences for which you kind of have a lot of like you have, which is bad looking upfront for the algorithm, but in the large time horizon.
Yes, but let's say I have an adder grid, let's say adder grid type algorithms. Then you have an adaptive bounds. Adaptive bounds is the square root of sum of the
Let's
loss
start.
square, right?
Yeah,
And
yeah.
loss square up to that round t. So this is something that I can compute.
Right. So, are you talking like in terms of can you aggregate? Okay, so that's something also you can consider. So you could integrate these two into, for example, small loss hedge algorithm. That's what you're saying. Okay, so in that case, you would get, let's say, minimum of these two regrets plus square root L star. That would be the ultimate guarantee. Okay. Now that square root L star can be, the loss can be very large. So, for example, if you have FTL and the data is, let's say, typical coming from Bernoulli a quarter, the loss of FTL is still n over 4. Its regret is very small, but its loss is still linear. So
Yes,
that's
sure.
why even if you have a small loss algorithm, you would like end up getting that extra square root L star. Which
Square root of n, yeah.
yeah, that would lead to this bound being vacuous, because in this case, in the case of a typical sequence, we would really like to get a constant regret. Yeah. So yeah, I hope this also answers your question about why we can't use multiplicative weights. Okay, so I'll just talk quickly about why we would like to use this formulation and how this is kind of different from what people usually do. So the usual kind of algorithms that people devise in this space will give you a guarantee of the following form. So they will give you one algorithm that achieves, for example, constant expected regret if the sequence is Bernoulli P IID and still having square root n regret in the worst case, right? So this is not a per sequence guarantee, and it's a bit hard to interpret because in practice, once you have a particular sequence, an algorithm of this kind is not able to tell you, what it means for the sequence that you have at hand, because it's very hard to kind of say, okay, this sequence came from, I don't know, maybe looks random or not. So this kind of guarantee is not only mathematically stronger, it's more interpretable in practice. And somehow this kind of instance optimality idea has not been considered so much, but like previous works either don't look very closely at fundamental limits of this gamma, typically require very, very specialized algorithms for the task at hand, and typically have no fundamental lower bounds on this competitive ratio. So that kind of brings me to the main result, which is fundamental limits on the competitive ratio. So for the upper bound, which is the achievability part, we have to show an algorithm that gives a certain upper bound. So we show a simple single switch algorithm that switches once from FTL cover and is able to achieve within 1.58 of the minimum of the regret of FTL and cover on every sequence. And this is kind of turns out to be a much more general principle than just binary prediction. And it tells us how we can integrate FTL with any worst case algorithm, not necessarily not necessarily cohort. So we'll see that. And when we have this, we also have this converse, which is a fundamental limit and shows us that if an algorithm achieves within a constant factor of these two regrets, that factor has to be at least 1.43. So there is some price that you have to pay in uncertainty for not knowing the nature of your environment.
Can I ask why is parameterized by n? I mean, why is it not just gamma star?
Yeah, so I had written this before because like a priori was not clear whether you could get something. So it's nice that we're able to get constant factors.
What is more general than mid prediction?
I will talk about, for example, online convex optimization towards the end, or any online learning problem in general. So right now we are kind of considering this very restricted action space of you have to predict a bit and your loss function is whether or not you were wrong. So in general, you could have any loss function, any action space. So for that, we can also tell you how to integrate FTL and any worst case algorithm of your choice.
Hi, I have a small question. So if you can go back to the previous slide. So here you have stated this regret explicitly in terms of FTL and power. So is there also a way to state this directly without using FTL and cover specifically? Like maybe Abhishek's favorite algorithm is neither of these two.
Yeah, so you can replace cover with anything else, but FTL is like FTL has to be kind of one of the algorithms. Yeah. So the idea here was like optimal algorithm for stochastic case, optimal algorithm for worst case. And we can kind of generalize this to FTL and any worst case algorithm of your choice, any robust algorithm. Okay, so any more questions before I get into the achievability proof? Okay. So to try to construct this algorithm, we are first going to try to look at what are the sequences on which FTL performs very poorly and what is it about these sequences that makes FTL perform so poorly. So I'm going to bring back this alternating ones and zeros example that we showed FTL performs very poorly on. And I'm going to draw the number of ones versus number of zeros versus the time t as the sequence goes on. And I'm going to rearrange the sequence and give you a sequence of exact same type, which is a very, very good sequence for FTL. Right? So FTL on this particular sequence incurs only half, regret half. So this is a bad sequence for FTL, this is a good sequence for FTL. And we see kind of sequences which hit the original lot seem to be bad and the ones that don't seem to be good. And in fact, this is in particular what we can show, that the regret of FTL on a sequence is the number of times it hits the origin divided by 2. And this is kind of going to be the main algorithmic building block of our result. So before we kind of get into the algorithm, maybe we can look at a proof of this. It's quite simple. So let's take this arbitrary sequence, right? So the regret of FTL is the mistakes, cumulative mistakes made by the algorithm minus the cumulative mistakes made by the best constant predictor in hindsight. So for this sequence, it ends with more zeros, so the best constant in hindsight is the all-zero predictor. Right, so now what we are going to do is we are going to decompose this cumulative regret into the regret of FTL over each cycle, where I'm going to define each cycle as going from one origin hit to the next origin hit. Right, so this is cumulative over all n. I'm just like splitting it up into the time peak chunks in between these line crossing. So now let's kind of look closely at the first one right here and try to see how FTL does for this particular sequence. But before we get there, let's think about how the optimal best in hindsight algorithm does. And by definition of a cycle, it goes from all like equal number of zeros and ones to equal number of zeros and ones. So the cycle will have exactly equal number of zeros and ones, right? And we can see here that there are exactly 3 ones and exactly 3 zeros. So what this tells us is that it doesn't matter like where the sequence goes after this. If I'm trying to look at the regret in just this cycle, the optimal is always going to make half the number mistakes, that is half the size of the cycle, right? So that kind of makes life easier for us because we know that no matter what happens in the rest of the sequence, no matter even what the structure of the sequence is like, the optimal is always going to make mistake half the times. Now let's look at what FTL does. So FTL will, at the very first time step, FTL makes a prediction uniformly at random and incurs a mistake of half. So here it does not incur any mistake because in this chunk, FTL is always predicting 1 because there are more ones than zeros. FTL makes a mistake, no mistake, mistake, mistake. So this is the full cycle. So the optimal always made 3 mistakes. FTL makes 3 mistakes at the 0 points, and then it also makes half a mistake at the first point. So the regret of FTL in this cycle is half. And in this kind of calculation, we didn't use any kind of how exactly are the y's progressing in this, or like not even the length of the cycle does not matter. The regret is always half in this cycle. So when we sum this up over the entire sequence, we get the regret is half times the number of times this sequence touches the origin. And the estimator, so remember how earlier I said that in the middle of the game, somewhat hard to know like how algorithms are doing. But turns out FTL has such a nice structure that we can estimate exactly how poorly FTL is doing so far by just looking at how many times my sequence has hit the origin. If my sequence has hit the origin a lot of times, I know that FTL is going to have at least that much regret, half that much regret, and so it's probably a very poor choice of algorithm for this particular sequence. Right, so again, this is very importantly, this is causal, so you can compute this after time step t. So that kind of brings very naturally the algorithm, which is just count the number of zero crossings, and as soon as they hit a certain threshold, switch to the worst case algorithm. So start off optimistically, and then as soon as you realize this algorithm is doing really bad, switch to the worst case algorithm as an escape hatch. So you start off optimistic, but you have some moat in the form of your worst case algorithm. Now, really, we want to choose the theta so that the regret gives you, the regret is within a small comparative ratio. And that is kind of the theorem that we can prove, which is that if you have a regret of square root n over 2 pi, you can achieve a comparative ratio of 2. But then if we randomize this threshold with this essentially an exponential distribution in 0 to square root n over 2 pi, we can improve this to e over e minus 1, which is 1.58. Okay, so now I'm going to get into the achievability proof sketch.
Can you go back to the last
Yeah.
So we are going to fix the threshold to be this theta, which is about root n.
Yes.
And then we're going to take a. Oh, sorry, there are the two. Oh, okay. So that achieves a gamma star of 2. Okay, sorry, I misunderstood. Okay. So that achieves a gamma star of 2, but if we allow a random thing around that, we can make the.
Yeah.
Okay.
Is there a way to get to run smart without knowing the horizon line?
Good question. So you can do it. And this is like what's called doubling trick in online learning, where you start with some horizon and once you reach that, you forget everything in the past and then double the size of the horizon, play your game again, and then carry on. You will kind of lose in competitive ratio. So you go from 2 to I think 12 or something. So you don't get a very tight control over the competitive ratio in that case, but you can do it. Yeah.
You would also switch multiple times between.
Yes. So like in each chunk, as you double, you switch once. So
sorry, is this switching idea something that is generally applicable to, like for example, suppose FTL is replaced by any other algorithm where I can guarantee that the regret is a constant factor of the number of zero crossings.
yeah, you could use the same idea, or like in general, if you can construct a monotone lower bound for the regret estimator, so that at time step t, let's say you're able to construct an estimator so that you know, okay, my algorithm has suffered at least this much regret. You can use the same idea. Yeah. Okay. So this is the proof for gamma equals to 2. And again, we start off with FTL, count the number of times my sequence is hitting the origin, and I switch to covert as soon as the count entry is greater than twice of this threshold. So, let's look at two cases. The first one is if there is no switch, then our algorithm is following FTL exactly throughout, right? And if there are no switches, it means there were very few zero crossings. I should have used FTL always anyway. So in this case, I am getting not within a factor of 2, but exactly the minimum of the two algorithms for this type of sequence. So if there is a switch at some point, it means that there were a lot of zero crossings. So cover would have been the better choice for this. So now I want to get within twice the regret of cover. Right, so for this, what I'm going to look at is just the regret of my algorithm is going to be the regret of FTL on the chunk before I switched and the regret of cover on the chunk after I switched. And by the definition of our switching rule, the regret of FTL on the chunk until I switched is half times this quantity, which is square root n over 2 pi, because as soon as regret exceeds square root n over 2 pi, I'm switching over. And the regret of cover on any sequence is length of that sequence over 2 pi. So doesn't matter anyway. So the regret is at most twice the regret of cover in this switch setting as well. So this was kind of very simple proof for how you get gamma equals to 2. And for general gamma equals E over E minus 1, this kind of idea of switching ones by constructing estimator connects to very classical algebra starting problems such as key rental. So if any of you work in this field, probably E over E minus 1, you already kind of understood where that comes from. Right? So yeah, so this is kind of the achievability. Yeah.
So you're using actually something stronger than regret, right? For cohort. So let's say I replace cohort with some online learning algorithm.
Yeah.
And let's say it has some regret guarantee.
Yeah.
But now you're using the regret guarantee starting from some random point.
Yes.
Right? So this is interval regret. So this is not the regret starting from the beginning.
Yes.
So you need an algorithm which is an adaptive with respect to the interval regret, which has interval regret.
Yeah. So you kind
the square root of the length of the interval. So,
yeah, so
it will not, for example, in hedge, if I replace cohort by hedge, it will not work.
No, it will still work because so hedge has a regret, let's say some square root n times some constant.
Yes, but
that's an upper bound. So,
yes, right.
So I can always say that regret of, let's say this was hedge, the regret of hedge on the next half of the sequence would be at most square root n minus t switch.
No, I mean, I don't think so, because for getting the square root of t log n bound for hedge, you start with some uniform distribution at the beginning. So if you want
some uniform distribution.
Yes, you initialize hedge with the uniform distribution.
Oh, okay, yeah. So you're right. At one point, we need to do this trick that you just forget about the past,
yeah,
and
so
you run edge
bound
only on that sequence. So like, yeah. So the regret in that case, I mean, this would be an upper bound because then you would have to change the comparators and all of that stuff.
Yeah.
But it would still work with this forgetting trick. Like once you switch, you forget about what you saw in the past, and then just play hedge on that chunk.
Right.
And on that chunk, hedge will always give me an upper bound of square root n minus t switch, and then that's always upper bounded by square root n. So then I will still.
That's why the time is so the sequence only from so the
algorithm
is like only when that's
right.
Yeah.
Right.
Yeah.
regret is also.
So.
Question, Rahul here.
Yeah.
So, given your algorithm is making only one switch,
Yes.
I don't see how you can use the doubling trick when the time horizon is not known, because as soon as you make the switch, now you're in the covert territory, and if I keep increasing the time horizon, you will only get the covert regret.
Yes, but then
so you actually have to make multiple switches.
Yes. So you start off with like whatever horizon size 2.
Yes.
Then in 0 to 2, maybe you switch once, then 2 to 4, maybe in that chunk you switch once, and then 4 to 8, you play a new game, and that chunk you switch one, and then
Right, exactly. So the algorithm actually has to change.
Yeah. So
not just the double. Yeah. Okay.
Yeah. So kind of you in each new epoch you forget the past, and then you just keep playing the game again.
How does the gamma really do this type of?
I think 12 or 14 or something.
It's bad, right?
That is bad. Yeah. So you can still do it, but like with constant gamma, but you lose very fine grained control.
Typically, the inflation is by factor 4.
Yeah. So I think because you're doing this forgetting thing, I guess there is some like extra overhead that you get. So
but there are anytime algorithms, right? Anytime algorithms, they completely avoid the doubling trick. So if I use anytime algorithm, does it work without?
No, because even if let's say you're using anytime hedge for the second algorithm, right? The first algorithm still needs the horizon length to switch. Okay. So that's why you kind of.
Why? Because the number of signs, like how many zero crossings you see.
Yeah. So
this is not anytime, right? FTX.
Yeah.
Is it based on the or is it like that a random walk on n steps you see about 10?
Yeah. You will kind of. I'm going to talk about the converse that will come up very cleanly. The converse.
Right. Good question. So if we were to replace cover with any other algorithm, then the switching will be essentially twice the regret, worst case regret of that
Correct.
other.
Yes, yes. So when you are kind of using this generally for any algorithm, you need some knowledge of how the regret, like you can make it with, you can use this doubling trick type, but you at least need like square root n or 2 times square root n. You need the function. So you need to know what is the function of regret, worst case regret for this other worst case algorithm. Yeah. In this one, it's very clean because everything is like same regret for every sequence.
Although I guess this is probably completely wrong what I'm saying, but so the thing you said that for FTL, the regret that you see for any sequence is completely characterized by the number of zero crossings. So, and turn out that FTL also has constant regret overall average, right? So I guess for me wrong, but would one try to say forwards that any algorithm or which has constant regret must have the property that on any sequence its regret is somewhat related to the number of zero crossings. Constant time.
Interesting. I don't know because the proof that we used for showing that FTL has half the number of zero crossings like relied very heavily on the fact that in each cycle you make a mistake exactly half the length of the cycle times. So I don't, I can't see how you would be able to get such a statement, but maybe it's possible.
Because the only reason why I'm thinking this may be possible is that in the stochastic model, the number of the fraction of zeros will concentrate around its mean.
Yes.
Concentrate extremely well.
Yes.
Therefore, a lot of sequences will have the property that the number of ones and zeros are kind of balanced by this peak.
Yes.
So can you somehow use this fact to say that?
I see. So you're saying like within each chunk, you will have like the P times the length of that chunk once or something like that.
Yeah, so yeah, you can somehow use this to say that.
Maybe I can't see it yet. So I was trying to think of how we can generalize this FTL proof, but maybe it's possible. I'm not sure. Anything else before I get into the converse? Okay, so this is now we will look at the converse proof, and this is like where the random walks part will come in if you like that. So, okay, so what we are trying to really say here is what is the extra multiplicative factor on the regret that any algorithm must incur, and we can show that any algorithm must incur competitive ratio of at least 1.43. So in particular, there is no algorithm that can on every sequence achieve exactly the minimum of these two regrets. So there is some unavoidable price for not knowing the nature of your environment. And the achievability that we showed is 1.58. So there is a gap here, and I'm not sure whether this is fundamental or there is some room for improvement here. So I would love to hear your thoughts if you have some ideas about this. And again, this is kind of the first hardness result in this best of both worlds setting that we know of.
What is 1.43?
1.43 is like what is
no, it doesn't just like e by e minus 1 is
no. It is something, but okay. I don't know whether it means anything, so I will do it now.
Okay.
Yeah. Okay. So okay, so now we need a fundamental lower bound for any algorithm. So we want to figure out what is some invariant property of any algorithm, and this is what we use. So if you feed any binary prediction algorithm a completely random sequence, Bernoulli half IID, at each time step, it will make a mistake of exactly half, right? Because P of y hat t is not equal to yt. If yt is Bernoulli half, is always going to be half regardless of what you're doing with y hat t, right? So expected mistakes of any algo is n over 2. So the expected regret is also going to be constant. And this is basically covert's regret. So covert is kind of getting equal regret in every sequence. This is kind of, if you're familiar, this is kind of related to Rademacher complexity ideas and so on. So the important thing to carry away from this is that the expected regret of any algorithm, the average over all sequence exactly the same. So now we're going to try to use this to get some fundamental lower bounds on gamma. So Again, if a regret achieves within gamma factor of the minimum of these two algorithms, I'm gonna take the average over all possible 2 to the n sequences on both sides and then get this lower bound. Right? So now for any algorithm, the expected regret is constant. By constant, I mean like depends only on n. And the regret of covert for any sequence is only depending on n. The regret of FTL is half times the number of times that sequence hits the origin. And now this becomes half times the number of times this random walk hits the origin. And then we can this is essentially now what we have to do to calculate this is to kind of look at this quantity, and this is something we can calculate the statistics of. And then we can simplify this. And then when we simplify this and take the asymptotics, we get this. I have never seen this before. I don't know if this means anything to you. So if it does, please let me know. But this is where you get the 1.4335 from.
No, how did you get this?
So you calculate this quantity. And then you kind of look at large n. This is basically, you can calculate the probability that there are exactly k zero crossings in from symmetric random walk, and then that is like you get n choose k type of terms over there.
Okay.
Just like
So approximation after approximation.
Yeah, a little bit of elbow grease here to get the asymptotics, but yeah, you can do this. Yes.
So initially I said that this framework allows you to do more than bit prediction. So the zero crossing idea seems very wired towards having zeros and ones. Maybe I'm missing. How do you
Yes.
generalize this?
Yeah, good question. So, FTL, the binary prediction case does poorly when you have a sequence that hits the origin a lot. In general, it does very poorly when your leader keeps oscillating a lot, or like when one leader where one quantity is overtaking the other a lot of times. If there is one clear leader, then on those type of sequences, FTL will do really well.
Is it formalized this statement?
Yes, so we can kind of construct the estimator that kind of looks at this. So yeah, so if you kind of have one clear leader throughout the sequence for general online learning, FTL will. So we can kind of construct the generalized estimator that reduces to half the number of zero crossings.
So the crossing was just the time when the notion of leader.
When the loss of both of them becomes equal, and when they both kind of enter into a tie, basically when one loses its clear lead. Okay, so this is experimental illustration. So I'm going to show you the performance of 3 algorithms, FTL, covert, and smart, in 2 settings. One setting which is more friendly to FTL, and another setting where we try to engineer sequences to mess up FTL's performance. So here, first I'm fixing horizon size to be 1000, and I am going to look at the expected regret for Bernoulli P IID sequences and plot that versus P. So what we can see here is that if P is kind of away from half sufficiently, FTL and smart are exactly kind of following each other. And then as you get sort of closer to half, both the FTL regret will shoot up, as well as like smart will kind of start deviating, because sometimes it will run into a sequence where it makes a switch. On the other hand, here is an attempt to kind of engineer a sequence that's bad for smart. And this is the following. We have this alternating zeros and ones up front, and then we kind of pad the rest of the sequence with all zeros. So in some sense, we are trying to trick smart into making a switch, even though it should not have made the switch. Right? So over here, if you have very few of these alternating zeros and ones, smart will follow FTL exactly. So I'm going to plot the regret versus the number of these zero crossings. If there are very few of them, smart will now make a switch. Then at a particular threshold, which is twice of square root 1000 over 2 pi, approximately 25. After this, smart will play FTL upfront and then over for the rest of the sequence. So immediately you have this extra cost. So, and you actually like for this type of engineered sequence, you can hit, because I'm doing deterministic here, you can hit that twice mark. So an FTL, of course, on this type of sequence, as you increase the number of zero crossings, keeps increasing linearly. So this kind of experimental illustration. So I think I will just briefly show you what happens with online convex optimization. So we were doing binary prediction. We can, in general, at time t, take any arbitrary action A and measure the quality of our action is measured by some arbitrary loss function LT. So this is kind of a general online setting. And in this case, FTL is exactly the same, which is the R min of the cumulative observed losses so far. You have a variety of worst case algorithms like the FTRL family, out of which one instantiation is this algorithm called online gradient descent. Right, so now again, I'm going to try to show you the performance in two settings, one more friendly to the average, to FTL and one less friendly to FTL. And the general idea of SMART is again to switch to from FTL to OGD based on a regret estimator that we construct. And this regret estimator is basically measuring how often the leader is changing. Right, so here is the friendly to FTL setting. Let's say at each time step, the function that we get is quadratic, right? So this is a strongly convex function. The FTL action is not going to change very much across time. So this is in some sense easy instance for FTL. And in this case, the online gradient descent regret versus the time horizon goes pretty much higher than what FTL does. So like FTL in this case is gonna have a much lower regret, and SMART and FTL in this setting are on top of each other. So you can't see those two distinctly. So in this case, no switch. This is a bad example for FTL, which is when you have a linear function and the gradient oscillates in each time step. So this is kind of the analog of that alternating 0-1 sequence, right? So you have a linear function, gradient is oscillating between 1 and -1 at each time step. And in this case, again, FTL regret increases linearly. The gradient descent, the gradient descent seems to be much more robust here, and SMART for small time horizons is gonna follow FTL, but after one point it's gonna be like, okay, too much oscillation in the sequence, just follow gradient descent. So this is kind of how the switch works in a more general setting.
So, but this is a strongly convex function, right? So
this one, yeah.
Yeah, so for strongly convex, we have logarithmic guarantees for
Yes,
it. So
yes.
then you have to change the threshold according to the logarithmic of t. Initially, it was square root of n, right? Now.
Yeah, so no, here you would again change with respect to square root of n, because we are trying to integrate FTL versus FTL with online gradient descent. So rather than constant regret versus square root n regret, we would say something like for easy loss functions, I want logarithmic regret, but for hard loss functions, I want to still be robust with that square root n factor. So we are still changing according to square root n, which is the regret of the worst case algorithm. But in this case,
the regret of the worst case that I'm saying, I mean, if it is a strongly convex, we have logarithmic guarantee. Regret is log of t, right?
Correct, yes. So in this case, when you have this loss function, there is no switch. Because you are only switching when you exceed square root n. But here FTL's estimator at any time step is going to grow.
So OGD is never played in the first place.
OGD is never played here. So you can see like you can't see because FTL and SMART are exactly on top of each other, but no switch here. Yeah.
And if it is like adversary somehow tailored, making it so that it switches and after that it is quadratic or also some way like that, then
yeah, I can imagine. I haven't plotted that, but I can imagine you can use the same idea that in constructing a bad sequence and achieve that two competitive ratio by putting like nice quadratic functions up front and then fooling it into switching too early.
Yeah. But the twice regret thing is still.
Yeah, twice regret is still, but kind of that's That kind of shows that the two factors you can achieve by engineering such a sequence.
Yes, so my question was, suppose I have a algorithm which is whose worst case degree guarantee is better than square root t. What is logarithmic or whatever t method. So in that case, can I still use your algorithm by changing the threshold?
Yes.
Okay.
Yes. You just need to know the function, and that function should be increasing.
Okay.
But you can do that.
Yes. Okay. And then the threshold is simply given by the worst case degree.
Yes.
Okay.
Yeah. I mean, because you were talking about small loss bounds earlier, you can also integrate it if the second algorithm has small loss bounds. So you can also but you have to do some extra tricks there. It's not that clean, but you can integrate it with that as well. Okay. So let me just summarize everything we did today, so I showed you how we can integrate any worst case algorithm essentially for free with FTL by constructing an estimator for FTL regret and switching as soon as you hit a threshold. And the competitive ratio that we can get is 1.58. So our algorithm will get within 1.58 times the minimum of the regret of these two algorithms. So we took kind of a very different per sequence perspective and tried to look into the per sequence regret landscape. And then later I spoke a bit about how we can make FTL compatible with any worst case algorithm. And there's also a fundamental characterization that no algorithm can achieve more than 1.43 competitive ratio. And this is a very simple algorithm, turns out to kind of be good for this case, which is nice. And so I spoke very briefly about both of this, which is how we can kind of use this idea for general online learning, and also how rather than kind of having our worst case algorithm to be something like a square root n worst case algorithm, we can integrate it with some more adaptive worst case algorithms like small loss algorithms, which you were mentioning. Okay, so couple of future directions. So one is kind of related to this, what I presented today, which is kind of bridging this stochastic and worst case dichotomy in sequential decision making. And I'm really curious about whether we can get instance optimal, best of both worlds bounds or bandit settings, how we can combine multiple algorithms, whether there are more algorithms with this kind of structure which you can calculate and so on. And you can estimate their regret and so on. Another area which I'm really excited about is incorporating noise resilience in decision making. So this is bringing back schematic from the first slide. So typically the feedback that you would get from the environment will come with some noise. So for example, imagine that instead of telling you when you predict what the next bit is going to be, the environment, instead of actually revealing the bit to you, the bit is coming to you through some binary symmetric channel, like it's getting flipped with some probability. You can imagine that in general, in practice, usually you might have some additive noise. You might have to quantize the feedback if you send it through some kind of wireless channel and so on. So the questions here become, how can we adapt our algorithms to noise? How does the regret fundamentally scale with the noise and so on? So two directions I'm super excited about. Okay, so that's the end of my talk. I will be happy to take any questions. Thank you. Yeah.
So the upper bound of 1.53 or 58?
58
is forward. Yeah, 1.58. Is this tied for the algorithm? I mean, is there any sequence where the algorithm does this? Can't do better than 1.58?
Yes, so I think so. We haven't so the two I showed you how to construct, but this one, it's slightly tricky because it's like randomized. But for example, in ski rental, this E over E minus 1 can be shown to be tight. So perhaps we can construct an instance. We haven't done so yet, but good question.
Given any algorithm, theoretically, this is precisely characterize this gamma for that algorithm.
Oh yeah, so for theoretically characterize this gamma for any two algorithms.
Yeah.
So I think that might be a
I think
challenging.
whatever you did was all empirical stuff, right? Like these curves that you getting are all like experimental things. So if you want to somehow like theoretically understand how this map works.
Oh, I mean, these two you can prove.
No, not the bounds. Exactly.
Oh, I see. Okay. So then you might have to kind of do some work with trying to construct, well, in principle, you would have to look at every single sequence and
Right,
see what is the
yeah.
worst. Yeah. So, but sometimes you can kind of try to construct like construct sequences that achieve. Like for example, I showed you how to achieve that too by constructing a difficult sequence. So yeah, sometimes you can kind of construct hard sequences knowing the structure of your algorithm. But yeah, I mean, how do you figure out general online learning, the worst sequence for any algorithm? There is some kind of work in this direction, but I haven't seen a lot. Yeah.
So at the end, you are really interested in the total loss function, total loss, right? Total loss of the algorithm. So I would like to compare the total loss of my algorithm with respect to the loss of the, let's say, these two algorithms, not directly in terms of the regret.
No, so are you saying that you want to?
So let's say I've got two algorithms, algorithm 1 and algorithm 2.
Yeah.
And let's say their loss functions are L1 and L2. This is a cumulative loss.
Okay.
So I want to construct an algorithm which is kind of whose loss is mean of less than equal to mean of L1 of L2 plus some order of whatever root t. This is a regret.
Right.
Because I'm interested in the loss that my algorithm, the algorithm that I construct, that suffers, right?
Right. So
it is not directly related to the regret of these two individual algorithms, but the losses. The regret is just a measure for their performance, right?
yeah, so you could say so we want are you asking how do we state the
No, I mean, this is a general question. So why are we interested in just getting the minimum of these two regrets? What I'm interested in getting an algorithm, designing an algorithm which suffers the minimum loss that these two algorithms suffer. So can I design an algorithm which is whose regret is given in terms of the mean of the losses?
Okay, so
I can just easily say that, okay, I can just construct two experts. These two algorithms are experts and just run a hedge on top of it. So
yeah, but if you would run a hedge on top of it,
Yes.
you would get minimum, the loss of the algorithm
Yes.
is minimum of loss of,
The
for
second-
example, FTL and cover plus the additional overhead
Right.
you get. Like even if you use a small loss algorithm, that overhead will be square root of L star, which
Right.
is the loss, of the better of the two algorithms
Right.
in waves. So even if the better of the two algorithms is FTL, that will incur n times p loss, right? So the final statement that you would get even with a small loss algorithm would be, here's an algorithm whose regret is equal to minimum of regret of FTL and cover plus square root n times
But
p.
not in terms of regret, in terms of the total loss. So if I just compare the loss that this algorithm suffers compared to the loss constructed to given by your algorithm, so can I compare the losses of these two algorithms? Because it is a total loss function that we care about.
Yeah, so ultimately we want kind of the loss to be gamma times
Yes.
No. So so if you have competitive with respect to the loss, that will be catastrophic immediately because let's say you are too competitive with respect to the loss of FTL and the loss of cover.
Yeah.
Right? So the loss, for example, of FTL, the loss scales linearly, but the regrets scales constantly. So if you are getting too competitive with respect to regret of FTL, loss of FTL and cover, let's say P was a quarter, loss of FTL would be n over 4. Already your loss will be like n over 2. So then the regret would start scaling linearly. So it's very important that we look at constant competitive ratio with respect to the regrets, not with respect to the loss. So was that your question? Also, like that was one aspect, and the other aspect is like using hedge will give you
If gamma was 1, then they will be the same thing. But right, because gamma is bigger than 1, your can sometimes give you a better because you're starting an
So if I run a hedge, because if we run a hedge on this 2, then the gamma is automatically equal to 1, right?
Yeah, but then you get extra square root
Yeah, but that is only square root of sublinear linear.
But
Yeah, but then
you subtract some factor of the loss also.
Okay, but
no, but then okay, so the loss that you would get is minimum of the loss of two sequences plus square root n,
square root of n, yes.
right? So that means that
But your algorithm will have like some constant factor of the loss of these two algorithms plus square root of n.
Mine
But then-
is some factor of the loss of the best.
Right.
so then you would kind of have the additional linear term there.
Okay.
So that kind of kills any guarantee that you might. So for example, if we used a hedge and tried to combine these two, perhaps it's easier to think in terms of the regret because there is such a stark difference in regret. So if you have a typical sequence for which FTL has constant regret and you used hedge, your guarantee would be the regret of my algorithm is minimum regret of FTL and regret of covert plus square root n. So minimum regret of FTL and regret of covert on a typical sequence is still constant, but then you have that extra square root n term. So if you already invariably have that extra square root n term, you might as well have used covert to begin with. So that kind of kills any gain that you might get. On the other hand, if you have constant times just minimum of regret plus maybe some like constant terms, then you still have like a constant regret for typical sequences.
So they're not comparable.
Yeah.
So just like this thing was about binary prediction. I was just wondering, suppose it was not binary but trinary or something.
Mm-hmm.
Like how do these? I mean, do the numbers get better? I wasn't able to get a sense of. Should I expect this 1.58 to become smaller? Or?
No, it will still be 1.58. But your kind of estimator will change, right?
Because
So,
I mean,
thinking that,
ternary includes binary in the special
Yes.
case, right? So you can't get smaller.
yeah.
Oh, of course. Okay. So then is the lower bound going to become better? I mean, like.
If you kind of tailor to ternary, perhaps the lower bound could be increased.
Because I was somehow thinking that, I mean, in many of these situations, I mean, the bad case is if there is no clear leader. I mean,
Yeah,
I'm okay
yeah.
with ties that are happening elsewhere.
Yeah. It does.
I see. So that won't improve the upper bound. Okay, gotcha.
So lower bound, so again, this lower bound is fundamental in the sense that binary prediction is a special case of any arbitrary online learning algorithm. So, the 1.43 will
So that
always
is
hold, but
okay.
perhaps you could kind of
You could
increase it a
increase
bit
the-
if
okay.
you only consider the other cases.
Okay, let's thanks Alankrita. She's here today and tomorrow and one month with more questions and stuff, right?
Just stop the recording.
Is it okay, guys?